Hello, my name is Giwon Bak. This is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. The topic that I'm going to present is a new machine learning-based approach for simultaneously modeling neural and behavioral data, named Gaussian process joint models. Before we get started, please note that a manuscript based on the research project being presented here is now in press with Proceedings of the National Academy of Sciences. As per the policy of PNAS, this presentation, as well as the accepted manuscript, is under embargo. The release date is not determined yet. You can always contact us by email. The first version of the manuscript is also accessible as a preprint. Recently, a joint modeling approach based on the hierarchical Bayesian framework has been applied to investigate the relationship between brain computation and cognitive mechanisms. Specifically, a component called a linking function at an upper-level hierarchy establishes a formal connection between the two modalities so that the information about the brain activity can constrain the behavior and vice versa. If we are interested in the underlying temporal dynamics of cognitive activities, setting a set of trial-level parameters is the most basic approach. However, this strategy can only offer indirect temporal constraints. The reason is that in the previous joint models, constraints are imposed only on the parameter space, focusing on finding the relationship between the parameters of the neural and behavioral submodels. There is no explicit structure defined for the temporal aspects of the model, and all the trial-wise parameters are treated independently with respect to time. Explicit modeling of the temporal dependency of the mechanisms of brain behavior and cognition can help us better understand cognitive dynamics within a task. Also, it is common to impose a strict assumption on the functional form of the linking function in the previous joint modeling practices. In both covariance and directed linking functions, the assumption of linearity between the two modalities are made, which is not guaranteed to be ideal in all possible situations. To address these issues, we propose a new linking function based on a Gaussian process that enables flexible, non-parametric modeling of the brain-behavior relationship motivated by Gaussian process latent variable modeling. A plot on the right side describes the basic idea of the Gaussian process-based joint modeling. Unlike previous joint modeling approaches, the latent variable models multidimensional temporal dynamics. The temporal changes in this variable are associated with the changes in the manifest variables, which are neural and behavioral observations. By using the non-parametric method for estimating the nonlinear manifold, we can have flexibility in modeling shared dynamics with minimal assumptions and can impose temporal constraints directly to submodels. From now, I will discuss the modeling strategy used in this study step by step. First of all, we need to introduce what the Gaussian process is. The goal of Gaussian process modeling is to estimate a function that explains data. In particular, the target function is modeled as a sample from a distribution of functions, which is characterized as a multivariate normal distribution. Gaussian processes model functions non-parametrically using an assumption that neighboring inputs are likely to generate similar outputs. The kernel or covariance function, denoted k, implements this assumption. The shape of a kernel, which affects the shape of the function, is determined by its hyperparameters. For example, a radial basis function kernel shown here has two hyperparameters. One is an output variance parameter, and the other one is a length scale parameter that determines the degree of similarity-based generalization. The distribution of functions is updated according to the observed data as illustrated in the plots. Given 5 observation points, you can find that the possible range of the functions is constrained after updating the distribution. When the kernel hyperparameters are known in a regression problem, there is a closed-form solution for the posterior distribution of functions. If it is not the case, the posterior must be estimated by maximizing the marginal likelihood of the model with respect to the kernel hyperparameters. The basic idea of the Gaussian process joint model, or GPJM from here, will be introduced. In the GPJM, a latent variable x is given a Gaussian process prior with respect to time. This latent variable serves as an input to neural and behavioral submodels to explain observed data. In principle, general linear models for neural data and cognitive models for behavioral data can be used as submodels similarly as in conventional joint modeling practices. However, in this study, we use two separate GP regression models as submodels. The use of neural data can bring up other practical concerns such as spatiotemporal modeling. Also, when using fMRI data, the hemodynamic lag is a crucial consideration because it causes a mismatch of the task-related timeline between the neural data and other experimental variables. GPJM can address these issues as well by using the Kronecker product and convolution of the kernel. To verify the performance of the GPJM, we performed two analyses based on a motion tracking task. I will introduce the setting of the task briefly first. We performed a motion tracking task using a joystick. In this task, participants continually reported the average direction of randomly moving dots throughout a trial, with a subset of the dots moving in a coherent direction to the left or the right. The degree of coherence and direction of motion probabilistically changed every second. In a simulation experiment, we fitted a fully spatiotemporal version of the GPJM based on a Kronecker separable neural kernel to a simulated dataset based on fixed underlying dynamics. Next, we fitted the GPJM to a subset of the dataset we collected from an ongoing study. Here, the GPJM was fitted to 16 regions of interest and a behavioral response vector. Note that ROIs were treated independently in this analysis due to the scalability of the model. Maximal a posteriori estimates were obtained for the latent dynamics and the kernel hyperparameters using gradient-based optimizer algorithms. In the simulation, we generated the data mimicking the task structure using two-dimensional dynamics specified in panel B, and the spatial and temporal kernels specified in panel A. Then we fitted the GPJM to the simulated data and investigated whether or not the model can recover the latent dynamics and kernels, not only fitting to the data well. Panels A and B show that the estimated kernels and dynamics are similar to the ground truth. Moreover, the model explains the data well according to panel C. In this simulation, 27 hypothetical voxels or regions of interest were generated. As in the temporal dynamics, we assumed that spatially adjacent voxels are likely to be more similar in their activations, but it is not the case for more distant voxels. We also added a simplification that the spatial and temporal dynamics can be modeled independently. These assumptions justify the use of the Kronecker product for making a spatio-temporal kernel, which is the strategy we used in the simulation. However, as the number of temporal measurements and signal channels increases, spatial-temporal modeling in kernel-based methods becomes quite challenging without appropriate approximation methods, which remains an issue to be addressed in follow-up studies. With this verification, we fitted the GPJM to a subset of the real data. Here we report the result from a three-dimensional dynamics model. Panel E shows the estimated dynamics. The orange dots on the 3D plot and the gray bands on the time series plot show the departure from the middle areas in the embedding space, suggesting that the estimated dynamics reveal the regular states and the deviations from them. Panel F shows the behavioral responses and neural data from two selected brain regions with the model prediction. As in the simulation, the fitted model explains the data appropriately. However, there is always a risk of overfitting in the model with extreme flexibility. Therefore, we performed a cross-validation analysis predicting a subset of the behavioral data given the latent dynamics trained with complete neural data and partial behavioral data. We randomly selected 1 to 4 consecutive data points per trial to test the performance with different sizes of test datasets. The structure of this analysis is illustrated below. We fitted 4 model variants with varying dimensionality of the latent dynamics from 3 to 6. The model with high posterior predictive density and low root mean squared error is supported strongly. The result shows that low-dimensional model variants are consistently preferred than high-dimensional ones. Then what could these dynamics mean? Although the interpretation of latent variable is not a trivial task, we could connect the topology of the dynamics to, for example, the patterns of functional connectivity. We clustered the time points of the neural data into 3 groups based on the degree of functional coactivation among 16 regions of interest we used. We could find that some time points with negative associations between the left inferior frontal gyrus and other brain regions are found around the middle area of the embedding space, while positive associations are more related to the departure from this middle area. In summary, GPJM can explain neural and behavioral data assuming that they emerge from underlying cognitive dynamics estimated in a non-parametric fashion. It can also address some important issues in modeling neural data, such as spatiotemporal modeling and considering the hemodynamic lag in the fMRI data. Finally, the estimated latent dynamics could provide meaningful insights for understanding the brain, behavior, and mind. A theoretical investigation is still needed to link the neural data and latent dynamics with the higher temporal resolution to a trial-level behavioral submodel. Also, fully Bayesian implementation using variational inference instead of maximum a posteriori estimation could allow us to make a better inference. Thank you very much for your attention. Please contact us if you have any questions.